Welcome to our presentation about self-optimizing application-agnostic multithreading for replicated state machines. I'm Gerhard Habiger, and the co-authors of this paper are Franz Hauck, Hans Reiser, and Johannes Köstler. The latter two are from University of Passau, while Franz Hauck and me are from Ulm University. We are talking about replicated state machines, so let's start with a very brief recap about state machine replication. SMR is a technique to provide high availability, low recovery times, and even achieve Byzantine fault tolerance. And we do this by having multiple replicas executing a service. That means that up to F replicas can fail without disruption. And each replica has to execute the service deterministically and has to have identical input. We achieve the determinism by usually employing single-threaded implementations, and we achieve the ordered input or the identical input usually by employing consensus between these replicas. Since we want to optimize performance of state machine replication, let's quickly look at the main factors of SMR performance. First, we have the speed of the consensus protocol, mainly how many round-trip times between replicas it requires to totally order the requests. Next, we have the execution time of the application itself, and we have network latency between client and replicas. For our paper, we will only look at the execution time of the application. So what are the main impacts of application performance in SMR? Well, the replicated application needs to be deterministic. As I said before, the easiest approach to achieve that is to use single threading. But of course, nowadays, parallelization is possible and also wanted because we want to utilize our multicore systems. Of course, we have to pay attention that the parallelization does not break determinism. And to tackle that problem of enabling parallelization while keeping the determinism, in the recent years, there have been two main approaches from our point of view. We call these request versus log level parallelization approaches. So let's first talk about request level parallelization approaches. That means that the granularity of parallel execution is always at the request level, meaning that incoming requests can either run in parallel to others or not. The decision whether a request can run in parallel or not requires prior knowledge about the application behavior. For request-level parallelization, there are different approaches. A recent paper by Alchieri et al. Classified these mainly into late scheduling, meaning that there's no client involvement and the decision is done after the ordering of the consensus system. And there's early and static scheduling. That means clients do participate in the decision, meaning they provide additional information with the requests, telling the replicas when to parallelize a request or not. An example for late scheduling would be CBase, and examples for early scheduling can be found in the LADC paper by Alchieri et al. Finally, an example for static scheduling might be PSMR. In all cases, we need a priori knowledge about the application, meaning that the developer has to supply the replicas with some information about which types of requests can be parallelized or not. In contrast to that, we have log-level parallelization approaches, meaning that mutexes protect the concurrent access to shared data. Thereby, requests can have multiple dependent or independent sections within one request, for example, meaning that we have finer granularity than with request-level parallelization, where every request on its own has to be independent or dependent of other requests. Therefore, we can potentially achieve better concurrency with log-level parallelization than with RLP, because we have more sections that we can run in parallel. However, we sacrifice linearizability with this approach. Instead of relying on a priori knowledge, as with the previous approach, we have a deterministic scheduler that ensures determinism, meaning that it orders the critical operations, for example, the locking of a mutex, during runtime. This has the benefit that we do not require any a priori knowledge about the application, as we did with the previous approach. Now, log-level parallelization approaches are not new, they have been around for a while, and usually they are statically configured, meaning they use a scheduler like PDS, which has been frequently used in projects such as dthreads, CoreDet, or Crane. PDS is a round-based scheduler, and it is statically configured at startup, meaning it is always the same round structure. I will briefly explain the workings of a round-based deterministic scheduler on the next slides while talking about problems that statically configured schedulers have, namely round-filling delays and unbalanced execution times. So let's first look at round-filling delays and meanwhile talk about how a round-based scheduler works. In general, deterministic schedulers look at the totally ordered list of requests after they have gone through the consensus, and a round-based scheduler picks a certain number of these requests that may then perform critical operations. In this example, we are looking at a deterministic scheduler that permits 3 threads per round to perform critical operations while blocking all other threads in the queue. These threads in this example want to perform one critical operation, namely a lock, and then they want to unlock. After that, they calculate for a while and then they terminate. Now we see that in a perfect concurrent round, all threads basically take their lock, calculate for a very short time and unlock, and then they can calculate in parallel, which means that the multicore processor has been utilized very well. However, since we are in a replicated state machine, the subsequent requests can arrive at a later time. For example, in one replica, the communication has been slightly delayed and the third thread has not yet arrived in the system. Since our round-based scheduler has been configured to include 3 threads in each round, it needs to wait for this third thread to start and finish until it can start the next round, meaning we have a big delay until the next round and the other threads can continue their execution. In this particular case, we can see that if we had configured the scheduler to only use 2 threads per round, the round-filling delay would be mitigated completely, but we would also leave some performance on the table in rounds where all threads are present. So in summary, the configuration of how many threads are included in a round has a big impact on performance. Allowing a large number of threads per round might increase concurrency, while on the other hand, it might increase the risk of round-filling delays. The second problem we have named earlier is the unbalanced execution time, and this occurs if we have different types of requests in the system. In this example, we have 2 different types of threads. The first 2 threads, 1 and 2, are the same as in the previous example. They just lock and unlock quickly and then execute for a certain time, while the third request also does a quick lock and unlock, but then has double the execution time. And including this third thread in the round increases the length of that round and delays the start of the next round, so delaying the other threads in the queue. Once again, in this particular example, this problem could have been mitigated by configuring the scheduler to only include 2 threads in the round. Both of these examples, the round-filling delay and the unbalanced execution time, show that the configuration parameter of how many threads are included in a round has a big impact on performance. So to solve the round-filling delay and unbalanced execution time, we could think of maybe reconfiguring the scheduler during runtime. That would minimize the impact of these 2 problems on the execution times. We call this approach dynamically configured lock-level parallelization, and of course we require a runtime reconfigurable deterministic scheduler for this. That is where UDS comes into play. UDS is our unified deterministic scheduling algorithm, which has been published in SRDS 2016, and it's a round-based scheduling algorithm and similar to PES in this regard. It has primary threads, which execute the critical operations during rounds. That's our terminology for the threads that are chosen to be in a round. And it can, of course, be reconfigured during runtime. It can be reconfigured for these 2 following parameters. It can change the number of primary threads per round, and it can change the number and order of critical operations that each primary can perform per round. These reconfigurations happen in between scheduling rounds, and this means that UDS is adaptable to the current system load and the application profile of the application that is executed in the replicated state machines. As I said before, we call this approach dynamically configured lock-level parallelization, and it means that we frequently reconfigure the scheduler during runtime to minimize the 2 problems that we have mentioned before. This, of course, improves system performance. At least that's the goal, and that's what we will evaluate later on. We have a couple of requirements other than the reconfigurable scheduler. The scheduler we already have, but we also need some kind of metric that we can use as a basis for our reconfiguration decisions. And this metric needs to be deterministic, of course. We also need a deterministic reconfiguration algorithm, so an algorithm that uses this metric to decide the reconfiguration of the scheduler. Let's quickly talk about these 2 points. First, we have a deterministic metric measuring some kind of performance point of our system. The problem is that we are measuring the system performance in Byzantine fault-tolerant state machine replication, which means it has to be robust against Byzantine faults. We decided to measure the throughput of requests and use that as the deterministic metric for our reconfiguration algorithm. And we do that by counting the requests per a certain time wall clock time interval in each replica. So then each replica sends these measurements periodically to all other replicas via the group communication system. That means that these requests with these measurements inside them are also ordered. Now, the main part of this algorithm is where each replica waits for at least m different measurements of n minus f other replicas, which would then deterministically yield identical groups of measurements in all the replicas. Here is a plot showing this, and I will explain our algorithm using this graphic. We have 4 replicas, R1 to R4, and each replica is sending these measurement requests, the little blue bars in these swim lanes, at periodic times. Not shown in this graph are normal other application requests, and you can imagine them dotted in between these blue lines. All of these requests are totally ordered by the GCS, which means that every replica will receive the measurement requests of the other replicas in a total order in between these normal requests. We have configured the m in our algorithm in this example to 2, which means that every replica will wait for 2 measurement requests of the other replicas until it decides to close this interval. We can now start our deterministic algorithm at t1, and every replica will wait for 2 measurement requests from n minus f other replicas. And you can imagine that every little blue bar that is being sent by every replica is received a very short time later at all the other replicas. And now we see at T2 that R4 has sent its second tick for interval 1, and all the others have received it. So that's the deterministic point where we could now close this interval. But actually our algorithm does a bit more behind the scenes, and then after that fact decides at time point T3 to retroactively close the interval after it receives the second tick of R3. So now that we have the interval closed at T3, the first interval is done, and we can now exclude the lowest and highest measurements to prevent Byzantine replicas from sending false measurements, and average all the remaining measurements together so that we finally have a deterministic estimator for the throughput. More details about this algorithm can of course be found in our paper. This is just a very brief overview, but suffice it to say that this is a deterministic algorithm to estimate the current throughput in a Byzantine fault-tolerant state machine replication system. With this, we now have one more step towards our dynamically configured log level parallelization goal, and we now only need the deterministic reconfiguration algorithm. Let's quickly look at this. We want to deterministically derive a new scheduler configuration using this estimated current system load as input that we have just described. And for that, we compare to the previously measured throughput and to also remembered performance of previous configurations, meaning that we remember our current and previous scheduler configurations and the performance that we have seen the system achieve with these configurations. Now we look whether the throughput has changed during the last n measurement intervals, and if it did not change, we just try scaling up because we assume that we are currently running at the limit of what the current configuration can do. If it did change, we keep the current configuration because we apparently still have some room to spare with the current configuration because the performance numbers are still changing. Or if it has gotten considerably worse, if the change in performance was a sudden drop in throughput, we scale down to mitigate the problems of round filling delays. Basically, This algorithm frequently explores the effects of reconfiguration, so it just frequently reconfigures and tries out new configurations, and then scales back to previous configurations in case the performance worsens, or keeps the new configuration if performance got better. So now we finally have all the boxes ticked for our dynamically configured log-level parallelization, and we can implement the system and look at what the numbers tell us. We have done this, and we have performed an evaluation with 4 BFT-smart replicas. We are using BFT-smart as the base of our system and extended it with UDS, our measurement mechanism, and the reconfiguration algorithm. All the consensus code parts of BFT-smart have been left untouched. Our entire system works after the requests have been totally ordered, so we did not modify any code in BFT-smart. We basically only added our own code. And we designed a variable workload that simulates the usage of, for example, a key-value store during a 24-hour period with a fluctuating workload. It looks like this. So it runs 300 seconds per measurement run, but is supposed to simulate a 24-hour usage period. So for example, during lunchtime and during evening, we have big usage spikes where up to 60 clients send their requests at the same time. And in the low load periods, we only have one client sending requests. The requests that are sent have fixed critical operations. That means we imitate a key value store using certain application load profiles in the requests. That means the clients can send different types of requests, and in the replicas we perform fixed number and order of critical operations, as we've seen before in the examples. So for example, a lock and an unlock of a certain mutex and a certain time that the request performs a calculation. For our first evaluation, we wanted to show and prove that the scaling of primaries, so the number of threads included in our scheduling round, has an impact on performance. So we measured using a statically configured scheduler without the reconfiguration algorithm, and we ran the workload against these static configurations. We see here the single-threaded version without any modifications, so that's vanilla BFT-smart, using a certain request type, and 7 configurations of our UDS algorithm ranging from 1 to 7 primaries. First of all, we can see that with one primary, we are not worse than single-threaded, so we are actually in the same ballpark. But we also see that with more primaries, we increase throughput dramatically. So having more primaries in high-load situations, so when there's enough threads to fill the rounds, improves concurrency and thereby performance. What we can also see in this graph is very interesting. If we have a look at the one primary configuration, everything seems kind of normal, except that the spike, of course, is not really a spike because we don't have much concurrency. But if we look at the higher primary configurations, we can see that the lower the load, the worse the performance is. And that's because of the round filling delays, because we do not have enough threads in the system to start rounds if there is a very low load. If, for example, we only have 1 or 2 clients sending their requests, but we have 7 primaries configured, that means we have to wait for another 5 threads until the round can start, which stalls all the other threads and cannot continue execution, which means we have extremely low performance. This is, of course, what we set out to mitigate in this paper. So on the next slide, we will show our optimized log-level parallelization approach. In orange, we can see our automatic scaling solution, while in blue and dashed gray, we can see the fixed configurations with 1 and 7 primaries, and the dashed dotted gray line references the right axis of the graph showing the reconfiguration decisions of our scaling algorithm. As we can see, when we compare the static configuration with 1 primary and our automatic scaling solution, our automatic solution always achieves better performance, especially during the high load periods. And what we also see is the fixed configuration with 7 primaries achieves very low performance due to round filling delay in the low load scenarios. We would also like to mention that the request level approaches would be roughly on par with the blue line in this graph, because the requests used in this evaluation cannot be parallelized on a request level. So in summary, our log level parallelization can provide additional performance, especially when compared to previous request level parallelization approaches, but also when compared to previous log level parallelization approaches. And our dynamic log-level parallelization is a drop-in replacement for the static scheduling solutions that have been used before with PDS. It provides better performance for variable workloads, and it provides more flexibility. For example, when the application profile changes during development of the application, we don't need to fine-tune a static scheduler. In future work, we could incorporate a priori knowledge similar to request-level parallelization approaches for optimal scheduling, and we can combine this approach with vertical CPU scaling for resource efficiency in state machine replication. I thank you for the attention, and I will hopefully see you in one of the next SRDS conferences.